This movie deals with the work energy theorem. It is intended for viewing before students do a laboratory experiment where the theorem is illustrated using measurements of forces on a cart moving on an inclined plane. Upon completion of the laboratory activity associated with this movie, students will be expected to be able to define and calculate work, differentiate work done by a force and work done against a force, define and calculate friction, normal force, and coefficient of friction, demonstrate how the coefficient of friction can be experimentally determined, and demonstrate the work energy theorem. If a force is applied on an object, we define the work done on the object by the force as F times S times cosine theta. In this equation, F is the magnitude of the force, S is the displacement, or change in location of the object, and theta is the angle between the force and displacement vectors. You will note in the example diagram shown here that there could be two possible values for theta. It doesn't matter which one we use as long as we follow a consistent convention. In the first diagram, for example, theta can be 225 degrees if we make our measurement starting from the S vector counterclockwise toward the F vector. But if we go in the clockwise direction, theta is negative 135 degrees. What is the value of theta in the second diagram? If you measure it, you should find it's about negative 53 degrees or positive 307 degrees. You will recall that the value of cosine theta can be between negative 1 and positive 1. This means that the value of work can be positive or negative. What is the significance of the algebraic sign of work? First of all, F times cosine theta is simply the component of F along the direction of motion. If we take the direction of vector S as the positive direction, then cosine theta is positive if theta is between negative 90 and positive 90 degrees. That is, the force is pointing toward either the first or fourth quadrant. The component of the force along the direction of displacement is positive, as shown here by the green arrow. We could say that as the object moves forward, it also experiences a forward push. In this case, work is positive. We say that the force is doing work on the object. What if theta is not between negative 90 and positive 90 degrees? In this case, cosine theta is negative. This means that the component of the force vector along the direction of motion is pointing in the negative direction, as shown here by the green arrow. We could say that the force is pulling back on the object as it is moving forward. In this case, work is negative. When the force is doing negative work, we can also say that the object is doing work against the force. Here's a simple example illustrating the calculation of work if we know the displacement of an object and the force acting on it. In this example, the object moves forward a distance of 3 meters. It is being pulled back by a force of 5 newtons. However, since the force vector is at an angle of 135 degrees, the actual force in the negative direction is only 3.54 newtons. We get this by multiplying 5 newtons by the cosine of 135 degrees. We can calculate the work by multiplying the displacement by the component of the force along the direction of the displacement. We get an answer of negative 10.6 newton meters or negative 10.6 joules. In this case, we say that negative 10.6 joules of work is done by the force on the object. Or we can say that the object did positive 10.6 joules of work against the force. In general, the application of forces on an object causes its speed to change. It can be shown that if the work due to all the forces acting on the object are added up, the sum is equal to 1/2 times the mass of the object times the square of the final speed of the object minus 1/2 times the mass of the object times the square of the initial speed of the object. This is called the work energy theorem. It is convenient to give a name to the value of 1/2 times mass times square of speed. We call it the kinetic energy of the object. Then we could state the work energy theorem more simply as follows. The net work equals the change in the kinetic energy. The total work due to all forces acting on an object is equal to the change in its kinetic energy. In this lesson, we will focus on cases where there is no net change in speed. In these cases, there is no change in kinetic energy. Therefore, the total work due to all the forces acting on the object will be equal to zero. The work energy theorem states that the total work due to all forces acting on an object is equal to the change in kinetic energy of the object. Sometimes it is convenient to exclude from the sum work that is due to what are known as conservative forces. When we do this, we need to add a term to the right-hand side of the equation. We call this the change in the potential energy of the object. Conservative force is one for which the work does not depend on the path taken to get from the initial position to the final position. An example is the force of gravity. The work due to gravity depends only on the initial and final elevation of the object. To move an object to the same height will involve the same amount of work due to gravity, whether you lift it vertically or push it up a ramp. Let's apply the work energy theorem to the lifting of an object. Suppose an object, initially at elevation y0, is lifted to elevation y. To make things simple, we will assume that the object is at rest. That is, has zero speed and zero kinetic energy at the initial and final positions. Taking the upward direction as the positive y direction, what do we know? First, we know that the average acceleration is zero. The speed is the same in the initial and final positions. In this case, it is zero. Next, Newton's second law of motion. Force equals mass times acceleration. This implies that the net force on the object is zero. This is because the acceleration is zero. The force on the object as it is lifted is shown in the diagram on the right. Obviously, there has to be a force pulling on the object upward. We also have the force of gravity, whose magnitude is given by the weight of the object, which is equal to m, the mass of the object, times g, the acceleration due to gravity. The downward force is negative mg, since we have defined the upward direction as positive. Since the net force is zero, the magnitude of the upward force must be equal to that of the downward force. In other words, the upward force is positive mg. We can now calculate the work due to the upward force. It's equal to the force mg times the displacement y minus y0. Since we have taken the upward direction as the positive y direction, y is larger than y0. Y minus y0 is positive. Mg times y minus y0 is positive. In other words, work due to the upward force is positive. How about the work due to gravity? Since the force of gravity is negative mg, work due to gravity is equal to negative mg times y minus y0. It is easy to see that this value is the negative of the work due to the upward force. The sum of the work due to the two forces is equal to zero, as expected, since the kinetic energy of the object has not changed. The net work is equal to the change in kinetic energy, which are both equal to zero in this case. Since gravity is a conservative force, we can exclude the work due to gravity from the sum of all the work, and identify it as the negative of the change in the potential energy. Since the work due to gravity is equal to negative mg times y minus y0, the change in the potential energy due to gravity is equal to positive mg times y minus y0, or mgy minus mgy0. This suggests that we can define gravitational potential energy as mgy. Here's an apparently simple question that actually requires several assumptions before it can be answered. Calculate the work needed to lift a 10 kilogram object to a height of 10 meters. First, we assume that there is no change in kinetic energy. Second, we assume that the given height refers to the change in elevation. Third, we assume we're on Earth. The work energy theorem states that the work required, excluding net due to gravity, is equal to the change in kinetic energy, which is 0, plus the change in potential energy, which is equal to the mass, m, times the acceleration due to gravity, g, times height, y minus y naught. When we push an object across the floor, then stop pushing, we find that the object eventually stops. The force that causes it to stop is called friction. Friction is a force that is due to contact between the surface of an object and another surface. The direction of the frictional force is always opposite that of the displacement vector. Consider the block shown here. What is the direction of the frictional force as the block moves from left to right? The frictional force is directed in the opposite direction. In the case shown here, as the block moves to the right, the frictional force is directed to the left. If there is no other force acting on the block, the frictional force will cause the block to slow down and eventually stop. If we take the left to right direction as the positive direction, the frictional force will be negative, and so will the acceleration. The simplest way to determine the frictional force is to measure other forces acting on it while it is moving at constant speed. Consider the cart moving shown here. We can tie a string to the cart and pull it to the right with force P. If we put the string over the pulley and pull down on the string with weights, the magnitude of force P will be equal to the weight pulling down on the string. We adjust the weight so that the cart moves at constant speed. We may need to give the cart a little push to get it to start moving, but if we want it to be able to determine the friction, once it starts moving, it should be moving at constant speed. Because the cart is moving to the right, the frictional force, F, is directed in the opposite direction. If the cart is moving at constant speed, then the magnitude of the frictional force is simply equal to the magnitude of P. Why? If the cart is moving at a constant speed, the force acting on it must be 0. For the net force along the horizontal to be 0, F and P have the same magnitude but opposite direction. Let's take a look at two other forces that are acting on the object. The Earth's gravity exerts a downward force on the object. The magnitude of this force is equal to the weight of the object. Since the object is not moving up or down, we could say that there is an upward force of equal magnitude that is also acting on the object. This is called the normal force. The normal force is the upward thrust that the plane exerts on the object. It is a known fact that the frictional force is proportional to the normal force on the object. That is, friction is equal to some constant times the normal force. The proportionality constant, usually represented by the Greek letter mu, is called the coefficient of kinetic friction. In this example here, what happens if we were to put loads on the cart to make it heavier? The normal force is equal to the weight of the cart and its load. A larger normal force would mean a larger frictional force. Since P equals F, if the cart is to move at constant speed, we will need to pull harder on the string to make the cart move at constant speed. The key to determining friction is to determine the other forces acting on the object moving at constant speed along the direction of the displacement. The net force along the direction of motion should be 0. That is, the magnitude of forces directed in the positive direction should be equal to the magnitude of forces directed in the negative direction. The direction of the frictional force is opposite that of the displacement. Consider the following problem. Suppose a constant force, P, of 20 newtons, is required to keep a 10-kilogram cart moving at constant speed to the right on a horizontal surface. What is the frictional force? Since the frictional force is directed to the left, and there are no other forces directed to the left, we could say that the magnitude of the frictional force is equal to the magnitude of P. The coefficient of friction is just the ratio of the frictional force to the normal force. The magnitude of the normal force is equal to the weight of the object, since there is no net vertical motion. In the preceding problem, we have identified the forces acting on a cart moving at constant speed on a horizontal surface. P equals 20 newtons. Theta is 0 since P is pointing to the right. That is, in the same direction as the displacement. The frictional force F is also equal to 20 newtons, directed in the opposite direction. So theta is 180 degrees. W, the force of gravity on the object, is 10 kilograms times the acceleration due to gravity, or 98 newtons. Theta for W is negative 90 degrees, or 270 degrees. The net vertical force is 0. The normal force, N, which is directed upward, is equal to the weight, that is 98 newtons. Theta for the normal force is 90 degrees. From these figures, we can verify the work-energy theorem by calculating the total work due to all the forces as the cart moves, say 2 meters to the right. The work due to P is 40 joules. The work due to F is negative 40 joules. The work due to W and N is 0, since these vectors are perpendicular to the displacement vector. Their components along the displacement vector is 0. Cosine of 90 degrees is 0. Thus, the total work is 0. This expected result, since the object is at constant speed, the change in the kinetic energy is 0. Here's an overview of the experiment you will be doing in the laboratory. You will determine the force of friction on a cart that is moving at constant speed on an inclined plane. For your first set of measurements, set the inclined plane at 15 degrees. You will need to weigh the cart. Put a 100-gram load on the cart and put it on the inclined plane. There is a string tied to the front of the cart. Put this string over the pulley at the top of the inclined plane and hang weights from the string. Find the appropriate weight so that the cart will move upward at constant speed. You may need to give the cart a little nudge to get it going. If the cart stops, you need to hang more weight on the string. If the cart speeds up, you need to lessen the weight hanging on the string. Next, adjust the upward pull on the cart by adjusting the weight hanging on the string, so that the cart moves down the plane at constant speed. Repeat this procedure with a 200-gram load on the cart, a 300-gram load, a 400-gram load, and a 500-gram load. Finally, repeat the procedure with a 100-gram load, but this time use a 30-degree incline. On the left is a picture of the materials you will use. You will use an inclined plane and a cart. Note that there is a pulley at the top of the plane. You will put the string that is tied to the cart over this pulley. You will suspend a hanger from the string and load weights on the hanger. When recording your data, make sure you include the weight of the hanger. Set the incline of the plane to 15 degrees, as shown in the picture on the right. Record the relative distance that the cart will travel along the plane and the height. As shown here, a distance s of 27 units along the plane would correspond to a change in elevation, h, of 7 units. You should be able to easily verify that h divided by s is equal to the sine of the angle of inclination. When setting up your apparatus, be sure to adjust the pulley so that the string is parallel to the incline. Push the cart to get it going. Once it starts moving, it should not slow down, stop, or speed up. If it does, you need to adjust the load on the hanger. If the load on the hanger is too light, the cart will slow down and stop. If the load is too heavy, the cart will speed up. Think of a systematic way of adjusting the load so that you're not just randomly guessing. Once you have determined the hanger load needed to make the cart go up at constant speed, adjust the load so that it will now go down at constant speed. You may need to give the cart a little push to get it started. Here's an overview of how to analyze your experimental data. Shown in the figure are the forces on the cart as it is moving up the incline at constant speed. F sub u is the tension on the string that pulls the cart up. This is equal to the weight on the hanger. The angle theta between F sub u and the displacement vector, the red arrow, is 0. W is the force of gravity on the cart and its load. Its magnitude is equal to the weight of the cart and the load. With respect to the displacement vector, you should be able to show that theta is 90 degrees plus phi, where phi is the angle of inclination. Except for the last run, phi is 15 degrees. For the last run, phi is 30 degrees. N is the normal force, the thrust that the plane exerts on the cart. It is perpendicular to the plane. If there is no motion perpendicular to the plane, it must be balanced by the force in the opposite direction. The force in the opposite direction is the component vector W along the axis perpendicular to the inclined plane. You should be able to show that this is equal to W times the cosine of phi. With respect to the displacement vector, the normal force is at 270 degrees. The frictional force is always directed opposite the displacement vector. That is, theta for the frictional force is 180 degrees. We do not know its magnitude at this point, but we relate it to the other vectors. Since the cart is moving at constant speed, the sum of all the force components along the inclined plane is 0. The component of F sub u is F sub u times cosine 0, which is simply F sub u. The component of friction is F. F times cosine of 180 degrees is negative F. The component of the force of gravity, W, is W times the cosine of 90 plus phi, or W times negative sine of phi. We know everything in this equation except friction. Thus, we have one equation and one unknown. When the cart is moving down at constant speed, the forces on the cart are shown in the figure. F sub d is the tension on the string that pulls up the cart. This is equal to the weight on the hanger. The angle theta between F sub d and the displacement vector, the red arrow, is 180 degrees. W is the force of gravity on the cart and its load. Its magnitude is equal to the weight of the cart and load. With respect to the displacement vector, you should be able to show that theta is 270 degrees plus phi, where phi is the angle of inclination. Except for the last run, phi is 15 degrees. For the last run, phi is 30 degrees. N is the normal force, the thrust that the plane exerts on the cart. It is perpendicular to the plane. Since there is no motion perpendicular to the plane, be balanced by a force in the opposite direction. The force in the opposite direction is the component of vector W along the axis perpendicular to the inclined plane. You should be able to show that this is equal to W times cosine of phi. With respect to the displacement vector, the normal force is at 90 degrees. The frictional force is always directed opposite the displacement vector. That is, theta for the frictional force is 180 degrees. We do not know its magnitude at this point, but we can relate it to the other vectors. Since the cart is moving at constant speed, the sum of all the force components along the inclined plane is 0. The component of F sub d is F sub d times cosine of 180 degrees, which is simply negative F sub d. The component of friction is F times cosine of 180 degrees, which is negative F. The component of the force of gravity, W, is W times the cosine of 270 degrees plus phi, or W times sine of phi. We know everything in this equation except friction. Thus we have one equation and one unknown. We have seen that from determining the upward force, F sub u, needed to make the cart move up the inclined plane at constant speed, we can determine the frictional force. In the equation shown here, W is the weight of the cart and its load, and phi is the angle of the inclined plane with respect to the horizontal. Similarly, we have seen that we can determine the frictional force by determining the upward force, F sub d, that we need to make the cart move down the plane at constant speed. We can combine these two equations to get a simpler formula for the frictional force. Subtracting the second equation from the first, we can show that the frictional force is just the average of F sub u and F sub d. Once we have calculated our frictional force, we can simply divide it by the normal force to get the coefficient of kinetic friction. We can average the coefficient of kinetic friction that we get from several runs, or since we use different loads on the cart for different runs, we can plot the frictional force versus the normal force. The plot should be a straight line with the slope equal to the coefficient of kinetic friction. Once we have determined all the forces on our cart, we can verify the work energy theorem. Assuming the cart travels distance s centimeters upward along the incline as its elevation changes by h centimeters, we can calculate the work due to each of the forces. We can ignore the normal force since it is perpendicular to the displacement vector. The work due to the normal force is 0. If we add up all the work, we should get a total of 0 since the change in kinetic energy of the cart is 0 when it is moving at constant speed. If we exclude work due to gravity, we should find that the total work is equal to the change in the gravitational potential energy. Once we have determined all the forces on our cart, we can verify the work energy theorem. Assuming the cart travels distance s centimeters downward along the incline, and its elevation changes by h centimeters, we can calculate the work due to each of the forces. We can ignore the normal force since it is perpendicular to the displacement vector. The work due to the normal force is 0. If we add up all the work, we should get a total of 0 since the change in kinetic energy of the cart is 0 when it's moving at constant speed. If we exclude work due to gravity, we should find that the total work is equal to the change in the gravitational potential energy.